Got it. Aloha, half a day. Thank you for the opportunity to speak to you. You can all hear me perfectly fine, I hope. Yes?
Yes.
Okay, great. Thank you. So Jane, why don't you, if you wouldn't mind, go ahead and we'll go to the next slide. Thank you for the introduction. So what I'm going to talk a little bit about is our changing climate, climate change, both climate change and variability, and then a little bit about what has happened with respect to climate and what is about to happen. And then some of the impacts in terms of not only the physical processes, but a little bit of the socioeconomic impacts. And then I'm going to kind of change tack and specifically talk a little bit about vulnerability and resilience of waterfront structures, try to target some of this information to this particular audience. I'm going to try to move through this pretty quickly to hopefully save some time for questions. So let's go ahead and get started. So I specifically started with the title and called it Changing Climate because it's very important to distinguish between climate change and climate variability. Climate change is really the trend of change. It's sort of the long-term response, if you like, to the external forcing, which in this case is an increasing concentration of greenhouse gases. And so that's something that's it's the signal, if you like, versus the noise. And so it's just moving along over time on the scale of years, decades, centuries. Superimposed upon that trend is a pattern or the variability, and that in this case is due to internal forcings. There's natural patterns of variability. One of the dominant ones in the Pacific is the ENSO, the El Nino Southern Oscillation. That's over sort of months to every few years, if you like. But it's more of a seasonal or short term, and there's other patterns of variability, but they're affecting the change. What's particularly important in the context of the Pacific and right now is that in many cases there's more happening in terms of climate change due to the patterns of variability than there is due to the trend. So that really the signal is less than the noise. Go ahead, and I'm on next slide. So let me just do very quickly talk a little bit about the climate variability piece. We have pretty strong predictability in this regard when I'm talking about ENSO. If you guys aren't familiar with what ENSO is, it's just kind of a graphic on the left. And the idea is that under sort of neutral and normal conditions, we have trade winds blowing across from east to west. They're literally piling up the water. They're piling up the warm water and the clouds, and that's sort of normal conditions, if you like. When we get an El Nino, that's basically when the trade winds are backing off. And so when the trade winds back off, all that warm water and all those clouds start to slowly slide across the Pacific, moving from west to east. And it's almost kind of a wave, if you think, a wave kind of essentially the rainfall starts at one end and moves across and ends up on the other end. And if it's a full-blown canonical El Nino, it hits the West Coast. Doesn't always do that, but sometimes it maybe stops in the middle, it doesn't get so far. La Nina is the exact opposite of that. That's when the trade winds crank up and they push everything even further to the west. And we've actually been in 3 years of La Nina right now. This is our third year, which is not super common. It's happened, but it's a fairly unique situation. So that's what we've experienced the last 3 years of La Nina. And what we've got on the right is showing that as that wave goes across the Pacific, in this case, they're in El Nino, there's a sequence of events that happen. And so one thing we do is we tend to get, my screen's a little harder to read even for me here. Let me try something. Well, what we tend to get is, first of all, wetter conditions as the El Nino develops, and sometimes in more tropical cyclones. And we're talking El Nino now. And in the case of like something like Guam, the sea level actually drops. and then the ocean temperatures in this case actually would decrease. And as a result of this happening, there's a sequence of specific impacts. So the beginning, if you like, a lot of the places in the Pacific Islands, the very beginning of it's very wet and it's flooding, and there's impacts related to sort of too much water. And then as those clouds pass over, you get a series of impacts related to not enough water, if you like. So it's drought, it's wildfire risks. The water's warmer at the later end, so you start to get coral bleaching effects. And again, the Red Cross just point out disease. So the idea is this compound event that has major impacts, and we can kind of get some predictability from it. I would know, just for example, going back to the point about the sort of signal versus the noise. During La Nina, the elevation of the water level in Guam is about a foot higher than normal, and in El Nino it drops as much as a foot. So you're seeing a huge amount, would be the equivalent of, like, if you're thinking global sea level rise, you're seeing a huge amount of variability in something like sea level just over these very short time frames. Next slide. So let's go through the climate change story then. I'm sure many of you have heard a lot of this, but I'm just going to summarize some information that much of which is captured in a report, the Pacific Climate Change Monitor, that came out in April, and I can send that to folks if they're interested. As I alluded to at the beginning, what we're talking about is really the change in the concentration of carbon dioxide and other greenhouse gases in the atmosphere. And so CO2 has been rising. Over the last 60 years, it's risen about 100 parts per million. So from around 315 to over 415 parts per million right now. And that's what you're seeing on the right, is a measure of the mean concentration of atmospheric CO2 at Mauna Loa. NOAA has an observatory there, the longest running historical observations of CO2 in the globe. And then underneath that are future concentrations of CO2 that are projections. And these all, this plot, we don't want to spend a whole lot of time on it, but the main point is that it's really hard to know exactly where things are going to go, because that kind of depends on what we do. If we continue at our current rate, and that's what you're looking at, the sort of the top one that's ramping and accelerating, that 400 parts per million could easily get up to 600 parts per million before the end of this century. If we institute some of the changes we've been talking about in practices like, reduction of use of fossil fuels, decreasing consumption of meat, things like that, to lower the CO2 in the atmosphere, then we could begin to kind of bend the curve and stabilize the CO2 levels. And so the extent of impacts really depends on what happens with these CO2 concentrations. Next slide. So CO2 is rising, and that really means that due to the greenhouse effect, that surface air temperature is rising and expected to continue to rise. The figure on the right is just a plot of the annual mean temperature across the Pacific over a baseline time period, in this case from relative to 1961 to 1990. And it's showing that it's increased by about 1.1 degrees centigrade, or a couple degrees, since 1951. If we plateau at sort of the 2 degrees C global warming, sometimes you hear that, we're shooting for 1.5, but let's say we get to 2 degrees C. That means for the Pacific, it's probably about a 3-degree Fahrenheit change is what we're likely to see by around 2050 sort of time frame. Again, it depends on what how high that's going to go. Depends on what trajectory we pick. Note that there's actually a little bit less ocean. This is the ocean temperatures, is what we're talking about, are a little less than the terrestrial temperatures, and a little less than the global average in the Pacific. Next slide. So air is getting warmer, so is water, and not just on the surface, but also through the whole water column. So again, we can measure this over the past few decades. The mean sea surface temperature across most of the Pacific has warmed by about 1.5 degrees Fahrenheit since 1982. One other related effect is marine heat waves, much like heat waves on the land, but in this case, warmer ocean waters have increased in duration, not necessarily in magnitude and not necessarily frequently, but it's just more days where the ocean's at a higher temperature. When we look at the projections for changes in sea surface and subsurface temperature, the lowest intensity heat waves and moderate heat waves are projected to increase from values of 10 to 50 days per year now to up to 100 and as much as 200 days per year along the equator. And this is, we'll talk about a little bit more, but this is the sort of thing that has huge impacts on coral reefs. It has impacts on fisheries, location of, where the fish are, their health, that sort of thing. Next slide. So we're warming the air, we're warming the ocean. That does a couple things. One, because the ocean's warmer, it expands. And then because land is warmer, it's actually melting ice. And so we're adding volume to the ocean. And so sea level is rising and expected to continue to rise. And unlike some of the other processes, sea level is a little bit slower. So we've got, and it's gonna keep going no matter what. So right now, since 1993, we've seen about 10 to 15 centimeters. So maybe around half a foot, 6 inches of change across portions of the Western tropical Pacific, and a little less than that in the central tropical Pacific. One outcome of that is we're beginning to see increases in what we refer to as minor flooding, so that you can think of like tidal flooding. We're starting to get those high tides every month. They're a little bit higher, and they're beginning to, rather than being maybe 1 or 2 days, they start to happen, 1 or 2 days a month. It might start to be the sort of thing that's happening 2 or 3 days a month, or even eventually 1 or 2 days a week. And that's what you're seeing in the bottom is just a projection of global sea level rise under different, under this particular emissions pathway, or under particular emissions pathways. The important thing to note here, 2 things. One is that, yeah, there's a real range at the out to 2100. Again, depending on the scenario we're looking at, it could be anywhere from 2 feet to sort of a 1.5 foot, let's say. But at least out to 2050, it really doesn't matter what scenario you pick. There's very little change. It takes time for those scenarios to diverge. And so out to about 2050, you're really only looking at about 20 centimeters, maybe 30 centimeters of change relative to that baseline time period. So sea level is a little bit slower happening than some of the other changes. Over time, it's going to keep going. It's probably going to keep, it's going to keep going for another hundreds of years, and eventually keep climbing to some of the higher values we hear people talk about on the order of 2 or 3 meters. Next slide. The conditions of the oceans are changing, and by conditions, I'm talking about things like chemistry and productivity. One of the measures that we look at for ocean chemistry is the oceanic pH, or the acidity, if you like, of the ocean. In this case, these are measures you're seeing existing, or what's happened historically. The decrease in pH, which corresponds to an increase in acidity, but a decrease in pH at Station Aloha, and it's been about equivalent to about a 12% more acidic relative to a 1998 baseline. Projections for ocean pH are for it to increase by as much as 0.3 pH under the sort of high emissions pathways. And the other concern is decreases in oxygen, or what we refer to as oligofiltration. In other words, basically less oxygen in the water, less nutrients, so lower chlorophyll concentration, so less productive ocean system over time. Some of this stuff is we don't understand super well all the feedbacks, and it's potentially a particular concern. Next slide. Last thing is the idea of the extremes are changing. So not just the mean sea level, but we're getting extreme events that are happening. It's a little harder. The rainfall is very hard to nail down, and because in some places it's actually showing drying trends, and other places it's increasing. It's partly because of that noise I talked about. The rainfall is kind of all over the place, and there aren't necessarily clear trends on where we think rainfall is going to go. Historically, we haven't seen much change actually in trends in the frequency or magnitude of tropical cyclones. So when we look at what projections look like in the models, it appears that there's probably not going to be more tropical cyclones. There just may be more tropical cyclones that are actually at higher intensity. And that's partly because as we've warmed up the ocean, we've got more moisture in the air, and we've got a hotter starting point. So there are likely to be more higher peak winds and higher rain rates. The balancing, it's not clear from the analysis, but what some people think is the numbers kind of look normal in terms of are there more or less, but it looks a little bit, and when you look at it more closely, it looks actually like the natural variability piece comes in. So there actually begins to be periods when there's less and more. So when you balance it out, it kind of ends up being, oh, there's not much of a change. But the suggestion there is that actually when you do have these years that years that favor tropical cyclones, you're likely to have more of those in those particular years. Next slide. So all these things happening are going to result in some societal impacts. One of those is decreasing freshwater availability. In some places, that's because there is reduced rainfall. In other places, particularly in the Pacific Islands, it's also because you're going to begin to get inundation, saltwater inundation in some of the limited aquifers. So that has again follow-on impacts to things like agriculture and just even community viability. So I kind of alluded to increasing flood damage with the idea of inundation, but you've also got impact from flood that's going to impact the coastal ecosystems. It's going to impact directly infrastructure, in particular things like port infrastructure. It's going to affect sectors like tourism and recreation. There's not, you have less beach to use if you like to put a towel on. Warmer oceans, less coral reefs. So coral reefs are not so nice to look at, that sort of a thing. And that's what I'm kind of alluding to again in the last one of these, declining marine and terrestrial ecosystems. So more coral bleaching, changes in the locations of ocean fisheries. So where are people catching fish? I think that's the sort of thing, again, that has implication to ports. How many fish are they catching? Let's see, increasing temperatures, I mentioned that, and that's just the idea that along with that, you've got, not only coastal reefs, coral reefs in trouble, but you're going to have, particularly in like places like Hawaii, where we've got these real, the relief, all these mountain habitats, if you like, that are fairly cool are going to begin to disappear as temperature rises. So a lot of things that live up in those habitats are not going to make it. Next slide. So when you kind of put all this together, you've got mounting threats to lives and livelihoods, potential for increased social strife, human migration, to make it increasingly difficult to sustain our economies and cultures. It's important to remember that, when we're talking about these changes, that it isn't just happening. It's not going to be the steady rise. There's actually going to be periods where maybe it dampens or slows down a little bit, or where it ramps up, in part due to this natural variability. So it gets amplified. So it's important to keep this natural variability in mind as we think about the overall change itself. Next slide. Okay, this is just a reminder for me, and I'm going to slide into a slightly different area. I think may have a little more direct after all the gloom and doom, let's see if we can get into something that's actually a little bit more actionable. And I think we'll have more, you'll be able to relate to more directly. Go ahead. Next slide, please. So what I want to talk about here a little bit is how do we get actionable information? How do we get information in folks like you guys' hands that you can use to adapt, to become more resilient to climate change? And so what I think we're after is wanting to understand, what's the weakest link, if you like, what eventful impacts are going to happen and when are they going to happen? And so to know that, we need to know a couple different things. First of all, we need to understand sensitivity. Sensitivity is basically just the weaknesses. We need to know what are the sorts of things that can happen in terms of the assets and infrastructure that I have. And then we need to understand the exposure, and that's the ability of the natural world to exploit some of those weaknesses that I have. When we combine sensitivity and exposure, we have a sense of vulnerability, and that's basically how likely are these weaknesses to be exploited. And knowing that, then we can start to think of like, okay, what sort of adaptive capacity, what resources, whether they're financial or technical, do we have to be able to reduce those vulnerabilities? Next slide. So I'm going to walk through an example. I'm not going to say exactly where this is all related to, but it's something we've done related to port infrastructure. When we're talking about that, we want to be able to think about not only the tropical cyclone sort of storm impacts, but we want to be able to think of gradual impacts. And in the context of sensitivity, the first thing is the idea of failure modes. And what I'm talking about by failure modes is that you can take the small boat pier on the right, and as we start to raise the water level, what's going to happen? In this case, you've got a floating dock on a guide pile or maybe a camel along the same sort of thing. And as we go up, the first thing that's going to happen that's going to have an impact is you're going to be bumping along the collars. And okay, I maybe don't have any damage, but it's high enough along that collar that I have some disruption. And that's an important thing here as we're thinking about, in terms of impacts, it's not just capital expenditures, but it's also downtime. The time is money. So in many cases, we want to know not only how much it's going to cost, but how many days of port time, for example, am I going to use? How often, at what point is my dock or my pier no longer functional? I can't answer that, but you guys can. But we can give you, you'll see in a minute here, we can kind of give you the numbers of a sense of like, is it 30 days? Is it 60 days? And when is that going to happen? Okay, so first thing I do is I bump up. I haven't broken anything, but it's close enough that maybe I get a little bit of rollover of the camel, or I'm bumping along the collar on my floating dock, and I probably don't want to do anything. Next thing I do, I go up a little higher water level, and I do begin to break the guide pile. I bust the collars, and I get some damage along that. And if I have underwater utilities, maybe I start to get some damage there. And then eventually the water level gets high enough that's going over the top of the deck. It's, in this case, it's completely blowing out the collars. It's potentially impacting the utilities, and if they're not protected at the top of the deck, and even damaging the deck infrastructure itself as you start to get some buoyancy forces pushing against the deck itself and kind of help detach it from its foundation. So that's sort of a sequence of failure mode that we're going to express as sort of a failure relationship, and that's what you're seeing in the middle picture is just this sort of simple stepwise. As I go up, here's what sort of happens, and you're seeing that then expressed as damage disruption state in the figure on the on the table on the left. So going from sort of fully functional baseline with no damage to, as I go from minor and moderate major, I begin to increase my damage and my downtime for, in this case, from 1 day to 30 days to 360 days a year. That's the amount of time it would take me to make, lost time, or the amount of time it'd take me to repairs and get functional. And then there's some cost as a percentage, or I can also do cost estimates as a percent of the replacement value for that particular structure. Next slide. So I've got sensitivity. I know what these key water levels are for this particular small boat pier. I know what those thresholds are. And now I need to know when I'm going to reach those thresholds. And so that's what you're looking at here, just very, very quickly, a couple of what are known the time series. It's basically just an hourly water level. And in this case, it's projected in the future. I'm not going to go into too much about the details behind it, but it's some fairly sophisticated analysis that enables us to generate essentially an hourly time series, or really Monte Carlo-like simulations, so we can generate, 10 or 20 versions of possible time series out in the future. And then in this case, we can add sea level rise to it. That's what you're seeing on the bottom. And so now we have the ability to sample this distribution to see how often it hits those threshold water levels that we talked about. Next slide. So what you're looking at on the left is what is, you may be familiar with the idea of a return level curve. In other words, what's the exceedance, the 100-year, you think of the 100-year storm. And so we can take those time series and sample those and get return levels. How high is, how high is the water level at 50, once in 50-year return, or once 100-year, once a 10-year. And so that's relevant for development of new port infrastructure, if you like, you want to know how high to design. But we can also begin to compare where our water levels, where our thresholds, if you like, our sensitivity thresholds, how are they relative to some of these return intervals? How likely are they? We can do better than that, and that's what you're looking at on the right. And in this case, it's just taking some pretend water, some pretend elevation, and saying, oh, well, we can actually look at over time how many times a year does it reach that elevation. And we can also look at not only how many times a year, but how long does it sit at that elevation? Because impacts aren't necessarily, if it touches it for some stuff blows up if it gets touched once. Other stuff needs to be impacted multiple times before it's, or underwater multiple times before there's a damage. So we're able to kind of look at not only the intensity, but the frequency and duration. So next slide. So going back to our thresholds then, this is one particular small boat pier. And what you're looking at in the yellow is the change in the the number of times per year over time that yellow threshold is exceeded. In other words, that you're starting to bump up along the guide pile collar. And then the orange is when you've blown the collar, so to speak. And this is just the hits on the, and you'll see it sort of increase. Notice towards the bottom, there's actually a little bit of a delay before it really starts to ramp up. And that's actually a factor of a function of some of the variability that's out there. In this case, it's a variability related to the tidal cycle. And if you look carefully, you might see another one of those kind of, it shows up a little bit in the yellow. But the point is that, again, that isn't necessarily the steady ramp up, that there are periods where it kind of slows down and speeds up. If you look on the right, that's really the one that really matters, because this actually has, one's just how many times it gets there. The one on the right is saying, okay, it got there, and this is how many days it got impacted. And so you see, because of that sort of, there's a tipping point there, in part because it's such a bigger deal when you blow the collars than when you're just sitting around them, that all of a sudden, that you only need a couple of those to happen a couple times before you've got a whole lot of downtime. And so we can get pretty narrow in terms of that, and when that happens in terms of the time frame, pretty specific sort of window of time, plus or minus kind of 5 years in this case. We can talk a little bit more at the end about how you can use this is sort of valuable information that folks like you guys can use to begin to figure out, well, when do I need to take action? Next slide. So on the right is still that operational downtime, and I blocked out some of the specific information on which period, the names of some of these particular assets. But what you're looking at is, we call it a heat map, but there's each one of those is either an individual small boat pier, dock, or boat ramp, and it's kind of the graphic summary of what you just saw before. It's showing you the downtime across a whole suite of port facilities, if you like. And you can imagine it being even larger than what we've got here. And so in this case, you're able to look and say, all right, the first two, the top two are the ones that get hit first, and there's actually some in the middle that maybe last a little bit longer. And I get some sense of like, okay, the numbers you're seeing there, the actual number of days per year that they're down. And you get some relative sense then of which of these structures start to be impacted and when they're specifically impacted. And then on the left, we went ahead and did the iteration. In this case, we did look at the money and we looked at capital expenditures. This is a fairly extreme scenario. It's 1.5 meters of sea level rise by 2100. It's in the year 2070, so it's fairly far down the line. There's some spread that's happened. But you can, and this is the same idea of these lists of different, in this case, different structures along the each one of those histograms represents a different structure, and the black line in this case represents the replacement value. And you can see that by 2070, for example, in most cases, every year you're getting damage that's twice the equivalent replacement value, except for maybe a couple of the facilities on the far right. Next slide. So to wrap this up and open up for any questions, with respect to some of the vulnerability, what we're really trying to do is get away from, I think, many of you guys, or state of practice lately or of late has been, somebody like me gives you a map of a flood map and says, hey, this is all underwater, go find out, figure out what to do with it. And there isn't really enough information in that to be able to narrow down and specify actions. So we're trying to reduce and bound the uncertainty down to the point of like, oh, right, okay, this dock or this pier is going to go in the next 15 years. And so that's, the first thing to do is extend the guide pile elevations. And that, depending on how high you'll get it, you may get another 20 or 30 years out of it. And then similarly, at some point, 50 years out, you're going to begin to have problems with your the whole dock infrastructure, and you may be differences among the different structures such that you can begin to kind of figure out which ones I need to target first, which or maybe I need to be looking at a whole new place. But we need that high level of granularity to be able to get into that level of decision making, that level of planning. And the last piece is just the idea of scenarios. I've really only kind of shown kind of an example of one, but we can kind of narrow that down and begin to say, okay, this is kind of the worst case, the best case. Again, the idea is to try to bring it in with sort of a window of within plus or minus 5 years kind of a thing, or 10 years kind of a thing. And even in terms of impacts, sort of tens of centimeters, that makes it actually something that you guys can build and design to. So I think that's it. I hope this has been interesting, and I'm happy to take any questions. You can go to the last slide. It's just contact information.
Thank you so much. That was very interesting. We do have time for questions. I'm going to take the moderator's prerogative and ask a couple myself. Dr. Marra, and I know you touched on this, but what do you think is going to be the first big thing to happen? I realize there's already been two storms, but what will be the next big thing to happen, and when? Look in your crystal ball.
Yeah, I mean, I think if we look at climate change, the big, what we're all kind of worried about writ large, it's probably not necessarily a sea level thing. It's probably more, I'd be more worried about heat. I'd be more worried about loss of coral reef and potentially changes in ocean conditions. That said, I think ports are actually in a uniquely vulnerable situation. They are going to feel some of these sea level rise and impacts first. They're certainly going to feel the increased impacts on infrastructure due to changing intensity of tropical cyclones, as well as the sort of gradual impacts of sea level rise. I suspect they're going to have impacts certainly in the Pacific Islands when things like the fishing grounds are changing. So where fish are landed may not be the same place that in the future that they are now, or may not want to be the same place from the standpoint of fuel and other kinds of costs. And just even then the issue of like how many fish are actually getting landed. So I think the ports are actually in kind of I don't want to say the canary in the coal mine, but there's certainly, a port is going to feel sea level rise before the land does, because it's just going to, that you guys are going to, it's going to start bumping things around before it ever starts to cover up roads and buildings and things like that inland.
True, which is why we, as who contribute to this problem in part, need to be making whatever changes we can in that area. Let me ask you just one other thing, and then we'll open it up. And that is, you talked about the negative impact, what some might call boom and doom, with good reason. Can you talk a little bit more about how that information can be used to support adaptation planning?
Yeah, I kind of tried to allude to that a little bit. Kind of the lingo these days is called, a lot of folks refer to as adaptation pathways. And so it's trying to figure out, it isn't necessarily an action, but it's sort of a suite of actions that are triggered as events take place. And so I tried in the last example show that if you have fairly detailed or some, the granularity information, you can begin to kind of map out an adaptation scenario. And you can begin to get a sense of like what resources are required to make that happen. So you can start to do some forward planning with this information. That's why the actionable is so key. If it's at the kind of level I'm alluding to towards the end. If it's just a flood map, with some, hey, here's the sea level rise, and it's, you got 3 feet of water, and on a contour map, I don't think that's particularly helpful.
All right, well, thank you. Do we have any questions for Dr. Marra? Yes, please, we have a minute. Zach. We're bringing the mic.
Thank you very much, Dr. John Marra, for those informative presentation. I've been watching and listening attentively. You speaking about the footprint of human activity on our planet, and most of the issues that you guys are tracking and monitoring is the carbon footprint. I just want to ask, I don't know if because there's no such stupid question on this. I just want to ask if you guys are monitoring whatsoever the evolution of the Earth around the sun and the rotation of the Earth on its axis and how it tilts, if it's tilting unusually or irregularly, is the speed of the Earth's rotation or the evolution of the universe. Does it have any kind of factor impact into the climate change, and how does it have correlate with the human activity?
Yeah, I think what you're alluding to, there are very long-term geologic cycles that, operating at hundreds of thousands of years that do have some impact on the climate, and they're recorded in ice. When we take ice cores and over looking back, you can begin to see some of those patterns. And but we're talking about as a whole. It's like they're just totally different scales and magnitudes of change. This is a change that what we're talking about in terms of CO2 concentration. These are changes that have happened like since well, maybe not Seinfeld on TV, but since TV. These are very, very short. These changes in the atmospheric concentration of CO2 are things that have happened extremely rapidly compared to what any sort of and the sort of other other forcings that you're talking about at these sort of geologic timescales.
Thank you. Yes, please.
Hi, Dr. Marra. Really great presentation. I learned a lot. One of the issues that's come up here is grant applications. And there are many, many different types of grants that Marra has available. There are also other sources of funding, but it seems like a lot of ports should be, especially the smaller ports in the islands, should be preparing in advance. We have a tough time of gaining funds right now. So is NOAA briefing MARAD, and is MARAD listening to the information that you just presented so that they can adjust funds so that small ports can be proactive in their projects?
So I'm going to confirm my ignorance and ask you to what you say, MARAD?
MARAD is the Marine Maritime Administration. And so they're the ones who are actually reviewing grants and approving grants for ports, you know, on projects or rail expansion. So that if you don't know it, then it sounds like those briefs aren't occurring and they need to.
Okay, I'm writing this down. I don't know if you guys can see that, but I'm going to route that up the chain. I'm sure there are folks that work this particular avenue more than I do, but that's a really good point. I'd be happy to, if as a follow-up to this, if you want to set up, we can set up some sort of dialogue. If there's some specific folks that we should talk to, please provide me any names and contact information, and I'd be happy to speak to them. And then also, more importantly, begin to try to make sure that those connections at the levels that you're talking about are actually happening. Because some of it may be my own ignorance, but I wouldn't be surprised if there's certainly some space for additional dialogue.
Thank you. And we do have another question, if we can get the microphone. We're here to the right, my right.
Dr. Marra, thank you for your presentation. I'm Richard Price with EA Engineering. And I was wanting to inquire, are you familiar with the Cosmos model? What are your thoughts on that sort of combining the sea level rise and wave and storm impact to this sort of analysis?
I'm not sure if I'm hearing it everything. I'm hearing you correctly. Are you talking about what we call total water level? So it's not just sea level, but it's also waves and even groundwater and all that sort of stuff. Is that correct?
Yes.
Yeah. So the information you saw, we actually are doing. So it's a good point you picked up. Thank you. A lot of the analysis to date is really what we refer to as still water level. You guys get that. It's basically just the water level inside the bay. It doesn't have any waves or run up on top of it. The analysis that we've been doing, we have got some techniques that we've been able to add. We do a total water level. So if it's an open coast and it's a beach, those water levels that you're seeing would in fact be a combination of the still water level plus the waves and run up. So that we've done through hydrodynamic models. So it is a total water level time series. It's basically the equivalent of the run up on the beach every hour. And then in this, I didn't show it, but we've actually have also connected it to hydrologic models, so we can run a groundwater model along with this. So you could actually you can be seeing what's going on in terms of your water table or your groundwater, and also things like your stormwater and conveyance, those sorts of things. But you can what I'm getting at is you can connect it to, you can also connect rainfall to this to help understand the extent of inland flooding, because I didn't mention that, but that's one of that sort of compound event, if you like, besides the waves, is the fact that, as you start to raise the water levels, you have much less freeboard or space for the water to go when it rains. So you have much more increased likelihood of ponding and inland flooding. So we can do that sort of stuff. Yes.
Thank you very much.
Thank you. Any other questions? Yeah. Another one coming.
Dr. Marra, thank you for your presentation. You talked about at the end about getting some of this data at the granular level to figure out how we can take proactive steps to protect our infrastructure. And I know you showed that example of the small boat dock, and I understand why you probably didn't want to say exactly where it was, but I think we may, as an association, benefit from knowing where these, where and when these occasions occur, what kind of money it's going to take to fix those or to start those projects and address them. And maybe NOAA can be a source of that information by asking permission from the various ports and facilities who are taking those steps to maybe post on the NOAA website where they are taking corrective action. That would be my request, please.
Sure. And so can that happen through the connection to the Maritime Administration? Or is that something, is it through this, is there the governing body of this group? What do you folks recommend as the best next step to begin to see if we can start to get information that you guys can use?
And that is an excellent question, which I certainly cannot answer. Is there anyone from EP that help us with that? No. So we're gonna find out the best way to proceed on that, and certainly let Dr. Marra know and let our members know.
And my contact information has been sitting up here for a while now. So if you're at all, if you want to reach out to me individually, please feel free to do that. Otherwise, I will circle back to you, Sharon or Jane, and anything that we can do is follow up. I'd be more than happy to try to take on.
That'd be great.
Thank you. Thank you.
I think the APP can play a role in a lot of the dissemination of the information.
Wonderful. Leave it in your capable hands, Jane. Okay, I think we have time for one more question. Are there any other questions? If not, I'll ask one question. I'm certainly not a scientist, so that I've said, there's no big question. When we talk about the carbon parts per million, is that including climate changing gases, other kinds of climate changing gases like methane?
No, if you include the other gases, are 416. Well, I said it's 415, 416 this year. I think it's actually more like 500 right now, because it becomes a carbon equivalent. So right now, it's actually, if you bring in the other gases, it would be equivalent to about a 500 part per million CO2. And it hasn't. We're approaching levels that we haven't seen in millions of years. Yeah. The last. So yeah.
No, thank you. Thank you so very much.